Doesn't work. I was amazed you could get it so quickly. So it doesn't work. A quick recap, we're doing this. So we are doing similarity transformations to observe, to sort of look at a system in a different perspective. So we are choosing a different state. And then by this change of state, mapping between x star and x, we actually can obtain significant simplifications in this new state space, where this is diagonal or Jordan form. Now, let's talk about the concept of eigenvalues and eigenvectors in this diagonal Jordan form. So we recap. We talked about what it means for if I do y equal to ax. We talked about the concept of if x is along the direction of one eigenvector of A, then y will be staying in that direction. It doesn't change direction, right? If x is along, let's say, vi, direction of one eigenvector, then y equal to ax equal to lambda I times x. Right? So let's say if x is equal to vi, then if it's along the direction of one eigenvector, then this will stay, the output y equal to ax stays in the same direction. Now let's put this into perspective for this system that we are talking about. So let's say, so consider the case, well, I don't have input. I just want to take a look at the initial response. When I release, let's say, the system somewhere at the initial condition x naught. So I want to analyze how the free response x equal to e at x0 will look like. So that's my goal for doing this analysis. Now, intuitively, let's say if the system is released at one initial condition that's along the direction of one eigenvector of A. Let's see what that happens. So if x naught, let's say it's along the direction of one eigenvector, let me call it T1. All right? So it's not immediately obvious how this will turn out. Right? If this is along the direction of one eigenvector of A, it is not immediately obvious how EAT times x0 will look like. Now, however, if we look at here, x dot equal to A times x. Right? So at the beginning, x dot, the initial velocity, initial derivative is going to be equal to A times T1. So what does that tell us? It tells me I am starting at some initial position, initial x0, and then the change that I will get for the state, which equal to A times T1, is also along that direction, right? If T1 is along the direction of one eigenvector, then AT1 is going to be equal to a scaling of T1. right? So this is along the same direction, eigenvector direction. All right? So that means we will not change directions if I start at the direction of a one eigenvector. So the velocity is along the same direction. I'm just accelerating along the same direction. So therefore, if I continue this logic, if initially my derivative is along the same direction, after I move a little bit, I am still in that direction, right? So let's say initially, let's say this is x1, x2, let's say two state. This is where my initial position, initial, let's say mass spring damper initial condition is right here. All right? So this is saying the velocity is along this direction. So I start here, and my velocity is also, let's say, is either going up or going down, but I'm along the same direction. So I may move to, let's say, here. And then at this new position in the state space, consider this. This is still in the direction of the eigenvalue. So the derivative, according to this definition, this system model, it is still along the same direction. So you will not change directions if you start right here. So it doesn't matter if I choose x1 or maybe there's another eigenvector direction, let's say this is t1 and then this is direction of t2. It is the same. If I start from here, I'm going to stay in this direction. So that's the conclusion we can draw from this eigenvector analysis. Now let's try to make more sense out of this one now. So let's go from this perspective and try to understand that it also makes sense if I look at directly this formula. If I start from the eigenvector direction, I'm going to stay in this direction. So this is observation 1. So our conclusion is if start along an eigenvector direction of A, then the state will stay in this direction. So the trajectory of the state will stay in that direction. It doesn't change. Now let's take a look at this one. From similarity transform, if I just take a look at the solution, what did we talk about in the last lecture? How EAT looks like after this similarity transform. From your notes, you should have something relating to T matrix and then lambda matrix. Say that again, please.
T inverse.
All right, so this is what we have. Let's say I do a 2x2 case just for simplicity. So 2x2 case, my T has 2 columns, 2 rows. And then my lambda, let's say I have 2 distinct eigenvectors. It's going to be E lambda 1t and then E lambda 2t. And then I have T inverse. And then my initial condition. All right? So let's say my initial condition x0, let my initial condition be in one direction of the eigenvector, let's say T1. All right, so what can we do here? Now there are two ways to do. The first is to take a look at this one. So it now equals to T1, T2, inverse, and then T1. All right, so just to do linear algebra, what does this one equal to? It's going to be actually something very interesting. So we know the fact. So I know T1, T2 inverse times T1, T2. I know if I do inverse times itself, it's going to be identity matrix. So it's going to be 1, 0, 0, 1. If I just take a look at the first column, then this is saying T1, T2 inverse times T1 is going to be equal to this 1, 0, right? So it's a fact. If you multiply an inverse matrix to one column of this matrix, then you get matrices, then you get column vectors that look like this, with 1 and 0. So if this is T2, then you get 0, 1. All right? So that's the first important observation. Now if you see that, then this matrix times 1, 0 is going to be picking up the first column. So therefore, you're going to get T1, T2. So first column of this matrix, E lambda 1, T 0. All right? So what does that equal to? Right? So you see immediately we are actually correct. I start at the direction of T1. I remain in this direction. The only thing that changes is going to be, because this is a time function, right? My state is going to move around. But it moves around according to this law, right? So E lambda 1t, the eigenvalue, is going to determine how fast your state trajectory moves along this direction of the eigenvector. All right? So same conclusion we can draw. Again, if the state starts along the eigenvector direction, then it stays in that direction. Any questions? All right. So that's nice. That's one way to take a look at this. So there's a slightly twist about this fact here. Yes?
Would you say that lambda determines the speed at which the response goes in T1 direction?
Right. So let's say in this picture, if you start at this direction, then by now we see that it's going to stay in this direction. Now, it stays in this direction, but it moves around. So this value here is going to determine how fast it moves. Let's say, let's do one example. So let's say this is my initial x0. So let's say lambda 1, let's say it's -1. So this is then saying as t moves on, you're going to scale this original vector by E lambda 1t. So if lambda 1 is -1, you're going to be going gradually to 0, right? So this is saying your state trajectory is going to do this. It's going to start here and then move to here. And how fast it moves depends on your eigenvalue. Yes?
So can we extrapolate this further and say that the system approaches points of singularity at eigenvalues, and hence they are also called as the poles of the system. And the eigenvalues are also the poles of the system.
Yes, so this is another way, this is actually a higher level view. So when we, let's say when we solve ordinary differential equation, what did we know? The poles of the ordinary differential equation, the roots of the characteristic equation is going to show up in these modes, right? So this is exactly similar concept. Actually, I'm going to talk about this a little bit more. So you already see the fact eigenvalues of a matrix relates to poles of the system, right? I'm going to talk a little bit more, if not today, next time. But that's a good observation. Now let's take a look at this in a different perspective. So we can take a look at this from this perspective. Now let's see the second perspective. I have T E lambda T, T inverse x0. So when we define the similarity transform, what is the relationship between between x and x star? So look at on the left-hand side of the board. X is related to my new coordinate, new state space by t times x0. So if you see that, then this goes away, becomes identity, right? So this is going to give you still t1, t2, e lambda 1t, e lambda 2t, and then you get this goes away. It's x1 star 0, x2 star 0. From here, you can see a different meaning of x star state, right? So if x star 2 is 0, then this is going to like this, right? So if this is 0, then you are picking the first column of this matrix, e lambda 1 t 0, and then multiply out, you get t1. So I can actually write the entire thing out, so we can see better. It's t1, t2. The first column multiplying x1, 0, plus the second column multiplying x2 star. So it's x1 star 0, e lambda 1 t, x2 star 0, e lambda 2t. The second part of the multiplication. So it equals x1 star 0, e lambda 1t, t1 plus x2 star 0, e lambda 2t, t2. So you can clearly see from this picture, from this result here, my response, my free response, you see, is decoupled into these two vector additions. The first vector is along the direction of t1. The second vector is along the direction of t2. And then they are scaled by, this is, we talked about this already. They're scaled by the eigenvectors, and then they are scaled by the initial condition in this new state, x star. All right? So this is coming back to here. What it means if when we say that I let my system start at one direction of my eigenvector, right? We said this is our choice. We let x0 to be t1. So what it means in this new coordinate system, in x star, it means what? It means this one is 0, right? In this new coordinate, new state space, the initial condition is 1, 0. It's picking this as non-zero and this is 1. This is 0. So you can understand the problem from either approaches. This more from linear algebra, this from the concept of decomposing a state into t times a new state. And then this new state space in this x star space, the first coordinate and the second coordinate, they are just the scaling of the solution space xt. So in the notes, I talked a little bit more about this. This one is equally helpful, I think. All right, so this is the concept of the meaning of eigenvector in system approach. So the key observation, the key assumption that I made today is actually this one. I say there are two distinct eigenvalues. Now in your homework, actually some of you already started and asked the question. In your homework, you will encounter a situation that you don't find two different eigenvalues. So how do we do that? That's the topic for the next part. So let's take a look at this example where we have a 2 by 2 matrix 1, 2, 0, 1. So let's see. Let's say what are the eigenvalues from here. So we compute, this is common practice. So for this one, if you do A minus lambda I determinant, you're going to get 1 minus lambda 2, the determinant of this matrix. So it's 1 times minus lambda square minus 0, because there's a 0 here. There are two repeated eigenvalues, both at 1. This typo here. So two repeated eigenvalues at 1. And if you compute, let's say, one eigenvector from here, so A minus 1t, A minus 1i is going to equal to, you can see here, right? So it's 0, 0, 2 times t1 equal to 0. So you can pick, let's pick t1 to be 1, 0. Pick the first column of this matrix. So it's going to be 0. That's one eigenvector. That's the only thing we can pick. You don't get a second linearly independent eigenvector out of this equation. So you cannot form our T1, T2 matrix from there. So how do we do the next? So we said the next best thing that's a little bit worse than diagonal is Jordan form. It turns out that if you do Jordan form instead of diagonal, so this is effectively putting us into this decomposition, right? So if I say this is J, we are doing this. So instead of a diagonal matrix, I have a Jordan matrix, lambda, lambda, 1 over here. And then things will work from this result, right? Let's say what it means for this formula to to happen. It means the columns, so this is A times the matrix, so it's a 2 by 2 matrix. It has 2 columns. Each of the column must be equal to the columns of the right-hand side matrix. So the first column is going to be A times T1 equals lambda times T1, right? Which is this, right? The interesting case is the second column. So this requires A times T2 must be equal to T1 times 1 plus lambda times T2. Or if you prefer, you can write it, you can shift the terms about T2 to the left and get A minus lambda I times T2 equal to T1. So you can put the numbers in and you will be able to find T2. This time you will be assured to get a solution. So let's see, A minus lambda I is still 0, 0, 2, 0 times T2, it must equal to T1. T1 is 1, 0. What kind of T2 is going to give me a 1, 0 here? It can be anything for the first element, but for the second element of T2, it must be 0.5 in order to make the equality hold. And then if you take a look at T1 and T2, you see that T1 and T2, they are linearly independent, right? T2 has an element in the second row that is no way can be expressed from T1. Therefore, these two, T2 is linearly independent from T1, and then you can put them up as T1, T2. This time, the inverse will exist for this T1, T2 matrix. So you see that T2 is related to T1, but it's not exactly computed in normal eigenvector computation. It is called a generalized eigenvector. So the computation, if you do anything that looks like this, A minus lambda I times T2 equal to a first eigenvector, right? This is the first eigenvector we obtained. If you generate a second vector out of this formula, then it's called a generalized eigenvector. Now this is the 2 by 2 case. For 3 by 3 case, it's very similar, but slightly different. So if it's a 3 by 3 case, if it's 3 by 3 case, we still are doing this decomposition, A equal to Tj, T1. However, there are different scenarios for the Jordan form if it's 3 by 3. So when 3 by 3 happens, let's say the eigenvalues are lambda m, repeated 3 times, then the Jordan form can have different cases. It can be like this. This is the perfect nilpotent matrix that we looked at, right? 1, 1 in the off diagonal here. But it can also be like 1 here and then 0 here, or 0 here and 1 here. So which of these forms we pick in this formula depends on the A matrix structure. So we'll talk about different cases in the next few slides. All right, so let's do the most straightforward, the best case that we can get. This is a case that I have repeated eigenvalues, but in the meantime, I also have T1, T2, T3. I can compute 3 linearly independent eigenvectors from this eigenvalue. So let's take a look. So the formula to compute this eigenvalue is like this. When we get lambda m, we compute the eigenvectors T from here. if this solution, if there are 3 linearly independent solutions, then we choose J to be this form, because we can fill T matrix directly from these original eigenvectors. So one example is perhaps, let's do, I have one coming up later. Let's do this one. Let's say A is let's do the simplest case. Let's say A is 3, 3, 3. All right. So I want to illustrate the concept that I can find. So for this one, it has 3 eigenvalues. I want to illustrate the concept that I can compute and get 3 linearly independent eigenvectors. So let's see. A minus lambda I times T equals to, so lambda is only 3, right? So in this ideal, simple example, you can see I have choices for 3 independent eigenvectors, right? I can choose, let's say, T can be 2, 0, 0. It can also be 0, 3, 0, right? It can even be 0, 0, any number, let's say 5. These will all give me 0 on the right-hand side. So if you put T equal to T1, T2, T3, stack them up together, you're going to get T equal to 2, 0, 0, 0, 3, 0, 0, 0, 5, and then T inverse. T inverse is going to be equal to, this is diagonal matrix, so its inverse is 1/2, 1/3, 1/5. We can check that this actually works. So if you do T times J, J is 3 by 3, so if T times J times T inverse, you can verify that it actually equals to A. All right, so this is a simple enough diagonal matrix computations. Yes?
So this only happens when A is already diagonal?
So this is a the most easiest example. I want to illustrate, you can find 3 linearly independent eigenvectors out of a matrix that has repeated eigenvalues. In reality, it may not be as simple as this. So A can be like numbers at the off-diagonal elements. Yes?
Why couldn't we pick T1 as something like 203?
T1, 2, 0, 3. Yeah, you can do that perfectly. So if you do that, what do you want to say next?
We can pick T1 as
Yeah,
something.
you can. You can perfectly pick this one to be, let's say, 3. So the key point is you still need 3 eigenvectors, right? If you choose 3 here, doesn't mean you can ignore this one. You still need something like this to complete the basis. All right. The main point is when you're given a matrix A and then you do this, if you can find 3 linearly independent eigenvectors, then you choose J to be diagonal. That's the best scenario you can get. So mathematically, this means what? This means, so I have a big matrix A minus lambda m I here. This means the null space of this big matrix has a dimension of 3, right? So T is in the null space of this matrix. And I can find 3 linearly independent solutions. So that means the null space of this one is 3. So if you want to compute mathematically, you can check by using this formula. If you want to find how many linearly independent solutions I can get from here, compute the rank of this matrix. If the rank, so it equals 3 minus the null space, like over here. If the rank is 0, then you get 3 linearly independent eigenvectors. So that's one approach you can get. So you can see in this example here, what is the rank of A minus lambda I? It's this one right here, so it's 0. In practice, you can check, do this first, and then see what is the dimension of the null space of A minus lambda I. You will be able to know like how many linearly independent eigenvectors you can get. That's the first case. So the second case is you have 3 repeated eigenvalues, and then the Jordan form may happen to be like this or this. So let's see under what circumstance this will be our choice of Jordan form. This happens when I still want to construct T, right? But it happens when T from the eigenvector solution, I can get only 2 linearly independent solutions. So let's say T1 and T3. So I only get 2 linearly independent eigenvectors, and I need 3. I need 1 more to make my T matrix to be invertible. It is in this case that we have this kind of Jordan structure coming up. All right? Let's see. This is A. Let's say I need another T2 matrix, T2 vector to make the whole thing work, to make this decomposition work. So this means A times this T matrix, right? A times this T matrix must be equal to T times this Jordan matrix J. So A times the T1 must be equal to lambda m times T1. And then this second vector, T2, A times T2 must be T1 times T times 1 plus T2 times lambda m. So this is the generalized eigenvector, how it's going to appear. So A3, A times T3 is going to be T3 times lambda m. So this is another linearly independent eigenvector we can get directly from the first step. So for this T2, you can see what we need, right? You can see that A times T2 must be equal to T1 plus lambda m times T2. So A minus lambda m times I, T2 must be equal to Ty. Yes?
Does it matter which eigenvector we get T2 from?
That's an excellent question. So I think yours, if you think about where this 1 appears, you will be able to know. You can choose whether T1 or T3. And if you choose T3, guess what will happen? This 1 will move to here. Yep. All right. I'll give you one more concept, then we will do one example, and you will see how this can actually be applied. So, all right. Here, the final piece is if you want to check mathematically when this scenario will happen, is again, this happens when after you compute A minus lambda I, you see like the dimension of this null space. If the dimension of the null space is 2, then you get 2 linearly independent solutions. So that's how you can do. So the last piece is this pure Jordan form, where you have this nilpotent matrix perfectly sitting in the off-diagonal elements. So this is the most challenging case. This is a case, if you do this computation, if you try to find one eigenvector, you can only get one. You can't get two, you can't get three. So this happens if the null space of this A minus lambda I matrix is only one-dimensional. You can only get one eigenvector out of this. So you have to generate both T2 and T3 from the generalized eigenvectors. If you take a look at the computation here, it's very similar in structure. AT1, AT2, AT3. T1 must satisfy AT1 equal to lambda m times T1. And then all the T2, T3 matrices are generalized eigenvectors. Now in this case, be a little bit careful. So A times T2 equals 1 times T1 plus lambda m times T2. That means AT2 minus lambda m times I times T2 must be equal to T1. T2 is a generalized eigenvector from T1. Now for T3, this is where you need to be a little bit careful. T3 satisfies AT3 equal to AT3 equal to 0 times T1 plus 1 times T2 plus lambda m times T3. So AT3 equal to T2 plus lambda m times T3, right? T3 is therefore a generalized eigenvector out of T2. It's like iterative process. You get T1 directly. This is this is the first eigenvector. Then you generalize 1 from T1. And then you use this generalized eigenvector to generate one more time. Get the third linearly independent vector for T matrix. All right? So let's do one example. If A is 2 by 2, and then we're going to do another one with 3 by 3 case. So this 2 by 2 matrix A, you can see the second column, the second row is the same as the first row. So it is definitely singular, right? It has eigenvalues at 0. So you can check. You can do determinant A minus lambda I is going to be equal to -1 minus lambda, positive 1 minus lambda, 1, -1. So it equals to 1 plus lambda times lambda minus 1 minus plus 1. So what it equals to from here? It is lambda square minus 1 plus 1. So it equals to lambda square. So there's only 2 eigenvalues. Both of them are at 0. Let's see what we can get out of, let's see how many eigenvectors we can get directly from here, right? So let's check the null space of A minus lambda I. So lambda is 0, so A minus lambda I is just A itself. So to check the null space of this matrix, -1, 1, -1, 1, right? So we're checking how many linearly independent vectors we can get by doing this, right? So you can see that one of the solution is this guy, right? Is the second element of the vector must be equal to the first element, right? Because the second column is negative of the first column. So the two elements in T must be the same. And then that's the only thing that we can get out of this. So the null space is 1, right? You can actually verify. You can verify the null space. You can check what is the rank of this matrix. The rank of this matrix is 1, right? So it has only one vector that is dominant. The second vector is generated from this vector. So it has only one rank. So the null space is also 1. So to be more specific, so nullity of A minus 0I therefore equals to the dimension of the matrix 2 minus this rank. And it equals to 1. So that is the one solution out of the direct eigenvector computation. So then, with this, we do a generalized eigenvector computation. So we do A minus lambda I times T2 equal to T1. So this is saying that negative 1, 1, negative 1, 1 times T2 must be equal to T1. So we can pick, let's say, the second column. So T2, let's say 0, 1 is going to give me the equality. So you see that T1, T2, they are linearly independent. So we can construct this coordinate transformation matrix T, and it has an inverse. Right? Because we are using generalized eigenvectors, so it has to be a Jordan matrix J. Right? So you can see that this actually works out. So T is this, you can compute the T inverse, and then it's going to be 1, 1, negative 1, 0. So the solution in the end is going to be, if you want to compute E AT, you can simply do T times this exponential function of a Jordan form, right? So it's E 0, 0, 0, 1 T, right? From the Jordan form solutions, this is equal to E times 0T, E times 0T, 0 T, E times 0T. So which is 1, 1, T, 0. And then you can multiply things out and then get E to the power of AT. All right, let's take a quick break. Okay, so let's take a look at this system and see what it physically means. If my A matrix looks like this, so that means x dot is going to have this relationship. x1 dot equals negative x1 plus x2, and x2 dot equals negative x1 plus x2. It is actually a symmetric system. If, let's say, following the logic of, if I start at one eigenvector direction, T1 is 1, 1, which corresponds to the eigenvalue of 0. So what it means, so this is saying I start at the initial condition x1 equal to x2 initially. From this formula of the model, we can see that if my initial conditions are the same, then I am not moving. Right? x1, negative x1 plus x2 is 0 for x1 dot, and for x2 dot is also 0. So if I start at this direction, I am not moving. what did we say about the eigenvalue? Eigenvalue is 0, right? So that means I'm not moving. I am not going anywhere. Following, if you take a look at any of the solutions that we did at the beginning, right? It is characterized by exponential function to the power of the eigenvalue. If lambda is 0, then this is 1, and I'm staying at this initial condition. All right? The intuition actually works. All right. So let's take a look at the intuition for 3×3 case when we have Jordan form. And see if I start at some direction, now this time not in the eigenvector direction, but in the generalized eigenvector direction, what will happen? What does that physically give us? So take an example. Let's say my Jordan form is like this. There's one generalized eigenvector, and then two linearly independent eigenvectors. From the Jordan form solution, we know that if J looks like this, then e to the power of jt is going to look like, it is still very much diagonal-like. So e lambda mt, e lambda mt, e lambda mt. And then for the element here, you get t times e lambda t. Right? So this is what you can recall from our computation, right? So you can also check by looking at this. So in this example, we take a look at ejt is 0, 0, 1. So it gives us e0t, e0t, and t times e0t. So for this 3×3 case, it is like you have So for this 3×3 case, it is like you partition the matrix into this. So you treat this as a block, and then this is the diagonal. This is diagonal to this block over here. And then you compute the block, the exponential function of the two individual blocks, right? Exponential of this is e lambda mt, and exponential function of this block matrix is e lambda mt, e lambda mt, t times e lambda mt. That's how the solution looks like, just from linear algebra. So let's go to visit the most interesting case. If, let's say, x0 is at one direction, let's say x1. Let's say it is along the direction of the first eigenvector, and see what will happen. So this is saying like this. So t x0, it is t1, let's say t1 scaled to by some number, x1 star. This is nothing but saying x0 is, I'm just redoing this step one more time. X0 is T matrix multiplying that, right, in the simplified state space. From there, we can see that this T multiply out with T inverse. So this whole thing is going to pick the first column of this matrix, right? If x star is this vector like this, x star 0 is this vector. So T inverse cancels out with T. So it's going to pick only the first column and then multiplying some scalar, x1 star. So if you start in this direction, if you start in the T1 direction, you stay in this T1 direction, right? If you do T times this vector over here, you get T1 times E lambda T, and then the scalar comes up to here. The same logic as what we did on the right-hand side of the board. So if you start in this direction, you stay in this direction. Now, if you start in, let's say, the generalized eigenvector direction in T2, let's see what happens. So in this case, you have something different. So similarly, it's the same logic. If x is T1, T2, T3 times 0, x2 star, 0, right? This again cancels out with T inverse cancels out with T. So the whole thing is picking the second column of this matrix and then scale it up by x2 star. So this time is not as simple as the first case. So what we're going to get is, let's say, continued from here. This equals T1, T2, T3 times T E lambda MT, E lambda MT, 0. So it equals to T E lambda MT, T1 vector, plus E lambda MT, T2 vector. All right. We started in the direction of T2. Now the result gives us we are not directly aligned with T2, but we are a linear combination of T1 and T2, right? So this is, if you start in the direction of a generalized eigenvector T2, T2 is generalized from T1, right? So if you start in this T1 generalized eigenvector, you're going to stay in the space spanned by T1 and T2, right? So because T2 is generated from T1, so it's related to T1. And if you start in this direction, you're going to stay in the subspace spanned by T1, T2. And it's independent from T3. Because T2 is generalized from T1. T2 is not generalized from T3. All right. Put it in words, this is saying the response does not remain in the direction of T2, but is confined in the subspace spanned by these two vectors. The eigenvector T1 we start with, and then the generalized eigenvector out of T1. Okay. So this is if I start with T2, which is generalized from T1. What do you guys think if I change a little bit? If J is lambda m, lambda m, lambda m, 1, 1, and I start in the direction of T2, and then the difference between these two cases. If I start at T2, what will happen? If I start at T3, what will happen for the solution? Have some guess. So let's take a look at the first case. If I start in direction of T2, what will my solution xt, what kind of space, vector space will I stay in? T1 and T2 combined, right? Because T2 is generated from T1. So this stays in the direction of T1 and T2. Combined direction. Now if I start with T3, then because T3 is generated from T2 and T2 is generated from T1, so they are all connected. So it seems reasonable to assume that this is going to stay in this combined space. So let's take a look. So using the same logic right here, right? So if my Jordan form is like this, what is EJT? Anyone can quickly check? All right, say that again, please.
E lambda and T.
All right. What about, what is this?
T squared by 2.
Half of T squared, E lambda MT, right? So this is EJT. Now, any questions?
Could you explain how you got half T squared?
Half T squared, it's from, the story can be long or short. Long story is we use Taylor expansion to derive this. And when Taylor expansion happens, for the square term, you have a 1/2. Yeah. So let's see. So in this case, EAT is going to be equal to T EJT T inverse times initial condition. Let's say my initial condition is in the third vector direction. So in the third direction of the vector, that means it's 0, 0. Let me choose, let's say, x3 star. So that's what it means if I start in the T3 direction. So this cancels out, and then we get T1, T2, T3 times this matrix multiplying this vector. So it's picking the third column, right? So you see the third column contains all non-zero elements. So therefore, the solution actually is in the space that spanned by both T1, T2, and T3. So our observation, our intuition is correct. All right. So that is the concept of generalized eigenvectors and how it impacts the system solution. Let's do the exercise on this whiteboard. Just a little bit hands-on practice. If A matrix, now this time is not as simple as we have used earlier. It is mostly non-zero in all the entries. So the question is, what are the eigenvectors? I already helped you a little bit and provided you the eigenvalues. So you have one eigenvalue at 5 and two repeated eigenvalues at -3. So let's see what possibilities can happen. Because I have two repeated eigenvalues, what can happen for my Jordan matrix?
Either diagonal or
Right? It's either this or have a Jordan form. So exactly which one happens depends on how many linearly independent solutions I can get from A minus this repeated eigenvector, right? All right? So that's something we need to do as a big picture. We need to do, for the first eigenvector, we need to solve A minus lambda 1t, lambda 1I times t1 equals to 0. And then we need to take a look at how many linearly independent solutions we can get from this. So for the first case, let's see. This is A minus lambda 1, so it's negative 2 minus 5. I'm going to omit the intermediate steps and write down the final entries here. And then 1 minus 5. And then 0 minus 5. 2, negative 3. 2, negative 6. Negative 1, negative 2. So what kind of t can give me this? All right. Any suggestions? 151. Let's see. How did you get that so quickly?
Because 7 plus 3 is 10 and 2 times 1 is 10.
All right. What about this one?
I am good at
Doesn't work. I was amazed you could get it so quickly. So it doesn't work. Right?
I tried.
Yeah, you tried. What is it? 511. Someone is saying 511. I'm seeing something. So if I do twice the second column and then combined with the first column, I get something related to 5. So let's try. I'm not exactly 100% sure. No. 2. So does this work? Negative 7 plus 4 plus 3 is 0. 2 minus 8 minus 6 plus 6. And then, so this is one of the eigenvector. Right? So we're good. This is T1. And then for this one, we need to consider A minus lambda 2. So it's negative 2 plus 3. It's 1. And then 1 plus 3, that's 4. And then 0 plus 3, that's 3. And then everything else is the same. So what kind of T2 can we get from here? This is
Column 2 is twice of column 1.
yeah. Let me double check. Did I make any typos? And this seems to be
1 minus 1.
right. So it's easy enough. 1 minus 1 can be 1. No, it's plus, right? This is one solution, right? So we want to see what else can we get, right? So what kind of tool can we use So I don't want to, in the end, this is something that I can do quickly by looking at the numbers, but you don't want to be guessing around when you see this kind of formula. You want some kind of criteria, right? What criteria did we mention about how many eigenvectors I can get? Say that again? Right? So we want to try to find the rank of this matrix, right? What is the rank? 2. Someone is saying 2. Any other suggestions? So you see, the second column is the first column multiplied by 2. And the last column is what? It's the first column multiplied -3. So you only have one really essential vector. So the rank is 1. So the null space is what? So null space is 2, dimension 2. That means you can get 2 linearly independent solutions. All right? So you get 1. We need to come up with another one. There's another solution like this. So someone is saying what? I need another one that's independent from this. Three, 0, 1, right? So excellent observation. You can see that if I already talked about the third column, it's the first column multiplied by -3. So you do 3 times the first column and then add to the third column, you get 0, right? You can actually do more. You can choose, let's say, 0, play around with this one. Actually, I can do this. 2, -1, 0 is going to give me the same thing, right? So the point is, either one you choose is linearly independent from this guy, right? So for simplicity, let me choose your proposal, 3, 0, 1. So therefore, by doing these calculations, especially this step, you know that the Jordan form is this one. So that answers one of you guys' earlier question, right? So for this matrix, that's seemingly innocent, and there's lots of non-zero elements, but we can still do diagonalization. So the T matrix is therefore, pick this one, pick this one, and then pick this one. And then you can compute the inverse, and then in the end, compute all right. So that's the basic idea of this one. Yes?
Can you explain one more time why the Jordan form is on the one on the left and not the one on the right?
Okay, so for this to happen, like this is the best thing we can get. This is happening if I compute T matrix. If I pick my T matrix, I can directly get 3 linearly independent eigenvectors out of these solutions, right? So this kind of thing happens only if I have some generalized eigenvectors. If I don't need to generalize a eigenvector, I won't need the Jordan block.
Okay, and what do you mean when you say generalize a?
Generalized means here. So generalized means, for example, here. If you need to compute some vectors based on a previously computed eigenvector, that is a generalized. All right. So for this case, so the main pieces are the Jordan form is actually diagonal. So not all right, based on our computation here. Okay. Okay. That is an excellent, another observation. So think a little bit more. What did we say when we say the nullity needs to be 3? What kind of J are we looking at in that case? So if you take a look at the notes, if it's lambda m, lambda m, lambda m, then you need the nullity to be 3. All right? So first, observe how many is actually repeated. If there's only 2 repeated, then you need this to be just 2. Okay, so once you get to understand the structure of these matrices, then you can be a pro control engineer. So you can do this. You can easily tell, like, if I give you a J that looks like this, what kind of solution is going to generate. So it's -1, -2, -2, 1, -1, -3, -3, and 1. So think a little bit and discuss with your classmates. Okay, I think most of you got it. I can hear the discussions. So what you see, actually I heard something even more exciting. Some of you mentioned face portrait. That's something I didn't teach, but you know. All right. Let's see. You can see these are just the 3 gigantic blocks combined together. -1, and then this block, and then this block. So this is a Jordan block. So we already talked about how if you do E, this one times T, how it looks like, right? So this one is going to give me E -3t, E -3t, T E -3t. Now, for the first block, it is also easy. This is like this. You can treat the whole thing as a diagonal matrix of 3 individual blocks combined together. So it's E lambda 1 t, which is -1. So for this one, this is a modified form, canonical form. This is this form. So this contains complex roots. So we talked about how to compute from here to here, and then this is the result, right? So if you don't remember how to do this step, do not worry. I'm going to provide you the most simplest case to compute EAT if A is like this later. So this is E sigma t -2t cosine omega t, E -2t cosine t, E -2t sine t, and then E -2t sine t. And then all the others are 0. So that's the solution for this blocked Jordan matrix. All right, so I listed some of the common matrix and then exponential functions of the matrix over here. Diagonal, Jordan, and then modified form. So all these are continuous time systems. Now, if we now take a look at the discrete time systems, is actually the technique are the same. So for discrete time systems, we have similar techniques. So we talked about the main thing is to compute a power of the matrix A. And then if A is similar, right? If A is similar to, let's say, a Jordan matrix J, then all the computations are very simple. So A squared is Tj T inverse times Tj T inverse. So since it's going to cancel out in the middle, you get Tj squared T inverse. So for the general case, you are just putting powers in J and then multiply T and T inverse on the left and on the right. So how you obtain the J is the same technique. You take a look at how many eigenvectors you can get from A. If not enough, generalize the eigenvector, put in Jordan form, such as these guys over here, right? Then you can compute JK. So some typical pairs are listed here. If it's diagonal, then the power of diagonal matrices are easy. Just the power of the individual diagonal elements. If it's Jordan form, then it is so similar to here. You get T times E lambda T. Then in the discrete time case, you get K, the time in discrete time, multiplying like a structure that's similar to the direct diagonal terms. So in the discrete time case, it's K times lambda power to the K minus 1. And then in the top right, you get, it's again some Taylor expansion result, half of K minus 1, lambda K minus 2. If you just have one Jordan block adding on top of diagonal elements, then you just need to do block separation and then compute the power of this submatrix, which is lambda k, k times lambda k minus 1. And if it's a modified form in discrete time case, you can get Rk is also sine and cosine functions, and these are the definitions. Again, there is a way to compute this one out of this J matrix, and I will talk about the concept. Let's do one exercise for the discrete time case. So let's say J is this, is one Jordan form, repeated eigenvalues of -1, one off-diagonal element. And then the second example is this, a lot of zeros, some kind of diagonal matrices, block diagonal matrices. All right. So you already know how to do the previous one. This one is very similar. So you treat this as a diagonal of these three submatrices and then compute the power of these submatrices individually. Right? So the solution, I will just work on this one, this 5 by 5 case. The solution is going to be lambda k for, let's see, for this one, lambda to the power of k, lambda to the power of k, and then k times lambda to the power of k minus 1. For this one, it's easy, it's lambda k. And then for the last one is using the formula on the previous slide. Using this formula, 2 by 2 matrix. So it's going to be Rk cosine k times theta, k times theta, rk sine k times theta, rk negative sine k times theta, rk cosine k theta, where k and r and theta are defined like this. So r is the square root of negative 100 to the power of 2 plus omega square, and then theta is inverse tangent of 1 over negative 100. So that's how the solution can be write out. All the other terms are 0. Okay. Let me give you the final piece that I promised. When you are looking at this one, so you can obtain this one using also tile expansion, but it's less straightforward. So the last formula I'm going to give you is specifically targeted for matrices that look like this. All right. So this technique is called the inverse transformation. So we know the solution to this x dot equals to ax plus bo, it looks like this, right? So the free response is EAT times the initial condition. So this is directly from the time domain solutions. Now, I already have a time domain function. I can do Laplace transform as well, right? So if I do Laplace transform, I can get to know the Laplace transform xs for the solution vector here. So this is, let's say, be a little careful. So Laplace transform of this vector is going to be s times x of s, right? Minus initial condition equals a x of s plus b u of s. So I can obtain capital X of s as just moving terms a little bit. S times I minus a, right? Si minus a capital X of s equals bus plus x of 0. So I can get to know what is the Laplace transform. Capital X of s is going to be Si minus A inverse times x0 plus Si minus A inverse times Bu, right? So I get to be able to know the S domain solution of the state. And I also know in time domain how it looks like. So it must be that if I do Laplace transform of this one, it's going to generate the solution here in the Laplace domain. In other words, EAT must be the inverse Laplace transform of this matrix Si minus A inverse, right? So x0 is here, so this must correspond to this one. So that's the main message. You can obtain EAT matrix by computing the inverse Laplace transform of this matrix. Questions?
Should that say forced response under the BU of S?
Oh yeah. Forced response. Thank you. All right. So with this, you can work on this one very easily. So if A is like this, then Si minus A inverse is Si minus A is going to be equal to S minus sigma omega negative omega. and then Si minus A inverse. Yep. All right. So Si minus A inverse, you just need to compute the 2 by 2 matrix inverse. That's easy enough. So it's going to be determinant in here, S minus sigma square minus omega times negative omega, so it's plus omega square. And the inside is S minus sigma, S minus sigma. I think I have typo.
I think the typo might be negative.
Yeah.
Because it's Si minus all of A.
Yeah, but
Oh, so
Your
typo
top
is
right
here.
entry should be minus. Yeah.
Yeah, so this is correct. It's still minus. Yeah, excellent. So you can do the inverse, right? So this one, you can compute the inverse of this Laplace domain quantity. Just look up the table. Then you can know that this is cosine, sine, and exponential. So that's how you can get this quantity quickly. So that's the continuous time case. For discrete time case is exactly the same logic. So we already talked about, like, from this we can solve the system in continuous time. The solution has the free response ak times x0 and then a bunch of summations. So if you do Z transform, right, you can also obtain the Z transform of the X response. So be a little careful in this time. So Z transform of this one is going to be Z, XZ, and then what? What is the initial condition part? So be a little careful. In the Z transform case, there is a separate Z standing out in the initial condition. So similarly, you can obtain what is XZ, especially what is the free response. Right? It's Zi minus A inverse times Z times X0. So this is the little separate term in the discrete time case. And then you can compare. This must be the Z transform of this part. So AK is the inverse Z transform of Zi minus A inverse times Z. All right? So with that, you can do this one in discrete time. Okay? So exactly same logic. Inverse of a 2 by 2 matrix, and then look up a table and obtain the time domain result. Okay, any questions? So this completes the picture of how you can obtain a continuous time or discrete time solution of a state space equation using these main pairs of Jordan form and exponential functions of Jordan matrices. All right? So let's see. I will stop here, and then next time we're going to talk about a new topic.